Have you ever looked at a really complex machine, like a robotic arm, and just wondered, how did they know it was going to move the right way before they even built it? Well, today, we're going to pull back the curtain on the fundamental formula that predicts motion. It turns even the most complex designs into a pretty simple calculation. Welcome to the Explainer.
So here's our game plan. We're going to start with the big idea, this concept of mobility. Then I'll show you the powerful, but actually simple, formula engineers use to figure it out. From there, we'll put that formula to the test on 3 different mechanisms. And we'll finish up by solving a really fascinating puzzle where the math seems to totally defy what our eyes are telling us. I mean, think about it. How do you even begin to design something like a car's suspension? You can't just throw some parts together and hope for the best, right? No way. It all starts with one single, crucial concept: figuring out exactly how a mechanism is supposed to move. And that concept is called mobility, or what you've probably heard of, degrees of freedom. Now, the most important thing to get here is that it's really just a number. That's it. This one number tells us exactly how many independent ways a machine can move. Is it just one simple motion, like a piston going back and forth? Or is it 6, like a super complex robot arm? Finding that number is everything.
So, how do we find that magic number? Well, we use this awesome tool called the mobility criterion. You should really think of this formula as the very first sanity check for any mechanical design. It tells you right from the get-go if your idea is even possible.
Okay, I know. This might look a little intense at first glance, but trust me, it's way simpler than it looks. It all just boils down to counting 3 little things in any 2D, or what we call planar, mechanism. So let's break down what N, J, and F actually mean. Let's just go through these one by one. First up, N is just the number of links. Those are the solid, rigid pieces of the machine. And don't forget, the ground, or the base it's attached to, always counts as 1. Next, J is the number of joints connecting all those links. And finally, F is what we call the connectivity of each joint. That's just a fancy way of saying how many ways that joint can move. A simple hinge that just spins, that has a connectivity of 1. Easy. All right, now that we've got the formula, the absolute best way to get it is to see it in action. So let's put our new tool to work and tackle a few challenges, starting with a pretty cool planar design. For our first challenge, we've got this 2-loop linkage. You can see it's got a bit more going on than a simple hinge. So the big question is, how many motors would we need to actually control this thing's movement? Let's use the formula and find out. Okay, let's walk through the steps. First, we count the links, N. We've got 7, and remember, that includes the ground. Next, we count up the joints, J, and we find 8 of them. Now, since all of these are simple rotating joints, their connectivity, F, is 1 for each, so the grand total is 8. Now, we just plug all of that right into our formula. And boom, the result is 2. So what does that actually mean? It means this mechanism has 2 degrees of freedom. In the real world, that tells an engineer they'd need 2 separate motors to control it. Maybe one motor drives it up and down, and the other drives it side to side. It's really that straightforward. All right, you ready for challenge number 2? Let's level up. This mechanism has a special kind of joint. It's a pin that moves inside a slot. Now, this is different from a simple hinge because it's got 2 kinds of freedom. It can rotate, sure, but it can also slide along that slot. Let's see how that changes our calculation. Okay, let's run the numbers. As you can see, we have 11 links and 14 joints. But here's the really important part. When we add up the connectivity, we have to treat that special joint differently. We've got 13 simple joints, so that's 13 times 1. But for our pin and slot joint, we have to add 2. That gives us a total connectivity sum of 15. We plug all that in, run the calculation, and we get a mobility of 3. So this more complex system has 3 independent ways it can move. This just shows how the formula can easily handle all sorts of different joints, as long as we're careful with our counting. So far, we've only been playing around in a flat 2D world, but what about real life? For our third challenge, we're going 3D. See, in 3-dimensional space, an object doesn't just have 3 ways to move, it has 6. It can slide along the X, Y, and Z axes, and it can rotate around each of them too. To account for this, our formula gets a simple but really important upgrade. That 3 just becomes a 6. Okay, check this out. This is a spatial mechanism. And notice the different kinds of joints. We've got spherical joints, kind of like your shoulder, a regular hinge joint, and even a cylindrical joint that can both spin and slide. The question is still the same though.
what's its mobility? The process is exactly the same, we just have to be extra careful with our joint types. We count 4 links and 4 joints, but let's look at that connectivity. A spherical, or ball joint, gives us 3 degrees of freedom. The simple hinge gives us 1, and that cylindrical joint, which can slide and rotate, gives us 2. Add them all up, our total connectivity is 9. Now we just pop that into our new 3D formula. And the final answer is a mobility of 3. This is just a perfect example of how flexible this formula is. With one tiny tweak, it works just as well for a complex 3D machine as it does for a simple 2D linkage. But what happens when the formula spits out an answer that just doesn't make sense? An answer that totally contradicts what we're looking at with our own 2 eyes? Well, we're about to investigate a famous engineering puzzle where the math seems to tell a very, very different story from reality. This is a Stuart Guff platform. If you've ever been in one of those high-end flight simulators, you've probably been tossed around by one of these. And just by looking at it, you can tell the top platform needs to move in every possible way, right? Up and down, side to side, forward and back, plus roll, pitch, and yaw. Your gut tells you that's 6 degrees of freedom. So let's see what our formula says. But when we get down to it, and we carefully count all the links and all the joints and run the numbers through our 3D formula, something really weird happens. We have 14 links, 18 joints, and a total connectivity of 42. We plug it all in, and the answer we get is 12. So here it is, our big paradox. The math says 12, but our eyes and common sense say 6. I mean, 12 degrees of freedom would mean the platform is just a floppy, uncontrollable mess, the exact opposite of what you want in a flight simulator. So what is going on here? Did our formula, this tool we've been trusting, finally let us down? Well, the answer is no. The formula isn't wrong. The problem is that it's actually too good. It's counting every single possible motion, even the useless ones. The solution to our puzzle is something called idle degrees of freedom. Think of these as movements that happen inside the machine, but don't actually do anything to the final output. Here's what's happening. Each of those 6 legs that connect the top and bottom platforms can spin freely around its own axis, kind of like a pencil rolling on a table. But that spinning, it doesn't move the main platform one single bit. It's idle motion. Our formula correctly counted these 6 extra useless spins, so when we subtract those 6 idle motions from our calculated total of 12, we get 6. Our formula was right all along. So in the end, this simple formula is basically the gatekeeper of mechanical design. It's that first critical step an engineer takes to separate a working machine from a locked-up pile of metal. It's the hidden math that dictates how our entire world moves, from the engine in your car to the robots on an assembly line. And it proves that the real question isn't just about what can move, but understanding the precise freedom that makes it all work.